Hello, and welcome again to Math321. I will be talking about Hermite polynomials. So, Lagrange polynomials are the unique interpolating polynomials through points. Which is wonderful. But what if you also know derivative information? So we know the value of the function, or we have estimates of the value of the function at certain points, and we have estimates of the derivative at certain points. Lagrange polynomials, we have no control over the derivatives. They go through exactly these points, but we don't know how to control the derivatives. Of course, in this case, we now have a lot more points than we had before. So the equivalent of the Lagrange polynomials, which uniquely goes through all of these points, which must be unique again by the same result, are called Hermite polynomials. And the unique Hermite polynomial that goes through these points has a particular formula, which I'll write down as a theorem for you. If f is C1 on some interval, and we have x0 up to xn inside the interval, are distinct, then there exists a unique polynomial h of degree at most 2n plus 1, such that hxi equals fxi, 2n plus 1, and h2n plus 1 derivative at xi is equal to f dash xi. The polynomial h2n plus 1 is given by h2n plus 1 x is equal to a sum from k equals 0 to n of fxi times a function which I will denote n comma kx plus another sum k equals 0 to n of the derivatives of our functions at each of the xk's, with another function times by another function I'll also denote with a subscript n and k, but it's h with a hat this time. So this looks a little bit like Lagrange interpolating polynomials, where the h's and the h hats here would be the Lagrange polynomials themselves. And that's very roughly what these things are. The hnk and the hnk hat are very roughly Lagrange polynomials. But they've been altered and modified in a certain way to ensure that not only are they 0 when x is different from xk, but their derivatives are 0. Well, this thing will have 0 derivative at each of the xk's, whereas this will have 0 value at each of the xk's, but will have derivative 1 at each of the xk's. So that's how it works. And the formula for these things are hnk x is equal to 1 minus 2 lots of x minus xk times L dash nk at xk times L squared nx. So if you plug xk into this term is 0. We end up with 1 times that, which is squared, at xk, and this will be the Lagrange polynomial, and the Lagrange polynomial at xk, of course, is 1, so 1 squared is 1, so this is value 1 at anything where xk is not equal to, where x is not equal to xk. Sorry, when it is equal to xk. When it's different from xk, this should be equal to 0. Why is it equal to 0 when we're different from xk? Oh, because this term here is 0. 0 squared will be 0, so that's 0. And similar logic applies to the h hats. So each h hat nkx is given by L minus x minus xk times ln kx squared. And here the ln k's x is equal to the product j equals 0 to n, j not equal to k, x minus xj over xk minus xj, which is the Lagrange interpolating polynomial. Sorry, the Lagrange polynomial, not the Lagrange interpolating polynomial. So a proof of all of this. So let's plug this in. For the reasons I mentioned before. That's either 0, whole thing 0, or this is equal to 1, in which case this term vanishes, then we end up with 1 times 1. It's great. We can take the derivative of this function. So here's my hk. If I take the derivative of that, I get, well, I take the derivative of the inside the product. So that will involve the derivative of this term, which is going to be minus 2 times L dash at xk, plus I get two lots of this times ln kx times L dash nkx. Plus, well, if xj is not equal to xk, then this term will be 0, so this whole thing will be 0. I've done something wrong. There we go. So this will be 0 if j is not equal to k, so that's 0, and this term will be 0 because that will be 0 if x is not equal to k. What if, so equals to 0 if j is not equal to k, and what if it is equal? So here h dash nk xk, well this will be minus 2 times L dash nk, whatever the derivative is, this value will be 1, so it's just 1, plus this thing here will disappear, so we get 2 times this evaluated at xk, which is 1, that's fine, L dash nk xk, and that equals 0. And I suggest you work through the details of this yourself. Because you can prove this as well. And these four results together give the theorem that we want to prove. Okay, we know a general error result for polynomials, and you can use that to calculate the error in this case. And it is f(x which apart from the squared term is exactly what you would expect based upon the previous error result. Proof of this involves exactly the same technique. Then count the zeros. And use generalized Rolle's theorem. Exactly the same as before. Why is there a w squared in here? Because you should do the calculation. There should be a double root at each each xi. It's a good idea to do an example. Start with some data, work out exactly what degree you're looking at, write down the formulas for all these things, calculate the values, etc., etc., etc. Do it. Try it. And the rest of the proof is an exercise. Give it a go.